why we need it. So we're on the network. We're on the network, and Alice sends some data to Bob. And if they're not in a local network, then Alice will send the packages towards internet provider. Then eventually it will reach the internet provider of Bob. And in between, there can be multiple machines. Every machine we call a hop. So every time you send something, it goes through a lot of computers running Linux there, and those computers do routing. And usually these are good guys, but eventually you never know. So especially the problem could be on the public networks, some Wi-Fi in airport, or maybe you connected to Swappie here. And are they trustworthy people? Do they look trustworthy? I mean, who knows, right? Serial killers also look trustworthy. So you never know. You want to protect. You want to encrypt, right? So Alice will encrypt the data and Bob will decrypt. What encryption is, it's basically some mathematics with your data. You're sending bytes. A byte is a number. You can work on a single byte at a time, or you can split your data into chunks. But basically, every chunk is still a number. So you can do mathematics. So a very simplistic algorithm is called Caesar algorithm, where you, for instance, to every byte, you add some number. But then Bob needs to apply some inverse operation. So Alice added, let's say, 10 to every byte. Everyone in the middle, all the service providers, they don't see the actual data. They see it encrypted. And then Bob needs to subtract the 10, right? Now, that 10 is called a key or a cipher. And the problem now is, how do they share that 10? Because somehow Bob needs to know that it's 10 that he needs to subtract. One way is for them to just meet and agree on a number, right? And in a very secure scenarios, maybe that's one of the possible ways. But of course, on the internet, this is not possible. Another way is just to send that 10 first before we send the encrypted data. But then someone in the middle will also see that 10, and they see a 10, and then they see some gibberish data. They can probably figure out what that 10 means. You can, of course, try to somehow obfuscate the data. For instance, send it in reverse, 0 and then 10, or something like that. This is called what is called security by obscurity, right? We try to make it very hard to figure it out, but a very smart person will still be able to figure it out. In most cases, no one cares about you. No one cares about your data, so you're safe. But if someone does care, they'll spend a week or two and they'll figure out what you're sending over network. So we cannot agree on the number offline. We cannot send that number. What do we do? And this is where Diffie Hellman helps us. It relies on very simple mathematics. There it is. If you remember from school, if you have a number and you raise it to a power of a, and then you raise it to the power of b, it's the same as saying m raised to the power a times b. Now, a and b is just a multiplication, and we know that in multiplication, the order doesn't matter. We call this a commutative operation. So we can write b times a. And then in terms mean that we could have first raised to the power of b and then to the power of a. Okay. So just to illustrate that this is true, we raise 2 to the power of 3. It means 2 times 2 times 2, and we repeat it 4 times. And eventually we have 2 to the power 12. If we first raise it to the power 4 and then to the power 3, then we have that and repeat it 3 times. So eventually we also had 2 to the power of 12. So how do we use it? Alice generates, so first again, the problem is we want to exchange somehow a number, and that number should not be visible in the network. So Alice generates some random number m and generates a random number a. A is our power. We said that we raise m to the power of a. A is a very secret thing. No one has to know about a. But m is visible, and we also calculate m to the power of a. And we send it to Bob. And in this case, as you can see, we send m, and we also send the result of this operation m to the power of a, but we never send a. Now, Bob knows m because it was sent to him. He generates a b. It's a random number, and it's very secret as well. He also can calculate and raise m to the power of b, and then send back. So now Bob knows what's m to the power of a is, and Alice knows what m to the power of b is, right? So now Alice has this. She can raise what she got from Bob to her private power a. And Bob has what Alice calculated, m to the power of a, and he can raise it to the power of b. And this way, as we said, is a commutative operation. They exchange a number, but that number was never on the network. Okay. Now, how do we break it? In order for attacker to break it, they need to figure out A or B. These are private numbers, or eventually this whole thing, because this is our cipher. The brute force approach would be, so the attacker knows that we raised m to the power of something and got 32. The attacker knows that m was 2. The attacker knows that the result is 32. What we need to know is that power a. How the mathematical operation is called when we want to figure out the power? Logarithm, right? So how do we get the logarithm? This is the brute force approach. We just take 2 because we know that number. We keep multiplying by 2, by 2, by 2 until we got 32. This is the brute force approach. In reality, the numbers are so large that it's impractical, at least for non-governments, to do that. Who can tell me what's the more optimal approach to figure out the power? The logarithm. Binary search. Thank you very much. So what we do is we know the 2, and we say, well, the 2 is less than 32, right? We multiply by 2, so it's still less than 32. Now, instead of multiplying by 2 again, we just square that previous number, and we see that to the power of 4 is 16, so it's still less than 32. Now we square that number, and we get 2 to the power of 8. We skipped all the intermediate powers, and we know that this number is now more than 32. Now we know that our true power lies somewhere in between 4 and 8. So we do the binary search. We first try 2 to the power 6. It's still more than 32. And finally, between 6 and 4, there's only one number. Its power is 5. So we now have the binary search approach, which in this case looks very like the number of operations is similar, but in reality, if we have a little larger, it's already a little more visible. So for instance, if we want to figure out the power of A, by the way, who knows already what's the logarithm? Thank you. Someone was very quiet. It's 31. Everyone should know that. So we have power of 1, 2, 4, 8, 16, 32. Now 32 finally is larger than the result of the powering. Now we do the binary search. Between 32 and 16, there is 24. Between 24 and 32 is 28. 30 is still less than. And then the final numbers between 30 and 32, it's 31. That's our power. So we actually have a very efficient way to calculating the logarithm. And this algorithm, the complexity is logarithmic, which is a coincidence. But yeah, so any attacker you can actually write this algorithm within, I don't know, spend a couple of days and write this algorithm and break the whole security of the world. So how do we protect ourselves? The key thing that this algorithm depends on is this ability to compare numbers. If we break this ability to compare, now this super efficient algorithm cannot be used. How do we do this? We use modular arithmetic or clock arithmetic. Basically, it's getting a remainder from the division, right? So you can scream 3 mod 12, 3, 13 mod 12, 1, 0, 0. So yeah, and yeah, for those who didn't hear about clock arithmetics, the reason it's clock is because it goes in rounds and rounds and rounds. So 13 mod 12 is 1 because we stepped 13 times around the clock and we ended up here. A little trick here. 11, yes. And by the way, this is not always how programming languages work. Why it's 11? Because we stepped 1 to the left, right? But some programming languages actually don't do this kind of mathematical way of modding. So if we take, for instance, Python as an example, yes, I have it installed. So -1. So Python does this mathematically. Also Haskell does this mathematically. But if we open JavaScript, we get -1. People probably don't see it. But this is more common for programming languages. C does it this way, Java does it this way, C++. So they remove the minus, do the mod, and then they stick minus back. I don't know why it's different in different languages, but that's how it is. Where's my presentation? There it is. Okay. And this is quite an important topic in programming. It's not just in cryptography where modular arithmetics is used, so we can practice a little and see where in real life we can use modular arithmetics. So for instance, if we have multiple computers and they can do some tasks, we don't want to run the tasks on the same machine. We want to spread those tasks evenly across 3 machines in this case. And we have 7 tasks. How do we spread it evenly? With a modular operator. Yeah, that's brilliant. So basically, we do mod 3 because we have 3 workers, and we want to spread this thing across 3, spread all the tasks across 3 workers. So we do mod 3. So it's going to be 0, 1, 2, 0, 1, 2, 0. Distributed databases can work this way. They can calculate the hash of a key, and they can, from this way, they know which node needs to store that piece of data. Hash tables like dict in Python, they also have to rely on a little similar approaches. Pac-Man. So in video games, sometimes we can, and in Pac-Man in particular, we can go to the right and we can reappear there. So suppose we are located at the X position, and now if it's larger than 1,000, we want to reappear there because we went that side. How do we do it? Thank you. Modular arithmetic. So let's say the position is 990. We add, when we pressed right, we added to the position 20. It's 1010 mod 1000 because it's 1000 pixels, and we will reappear at the position with 10 pixels. And what's nice in the actual mathematical operation is that if we do the minus, if we here, when we press left and we do minus 20, so if we were in the position 10 minus 20 mod 1000, will reappear at 990 right here. And also a cool example. Kids really like it very much. So today is 26th of September, and it's Thursday. Don't look at your phones. You have to figure out what's going to be the weekday on the, let's say, 27th of October. And don't scream first. Don't tell anyone. I'll give you some time. 27th of October. Today's 26th of September. It's Thursday. Okay, now I'll count and you'll have to scream. 1, 2, 3. Yay! I like these loud responses. So I actually heard one person say it's Sunday. So let's check. We have 4 days left in September, and we have 27th of October. So it's together is 31-day difference between now and 27th of October. We do the mod 7. So 31 mod 7 is 3, right? Right. So it's 3 days from now. So it's Thursday, Friday, Saturday. Yeah, it's Sunday. Let me double check. I got it. I actually got it right. Well, not me. Yeah. Okay, so that's modular arithmetics. So now instead of sending the actual number, we need to come up with some mod, with some modulus, and get the remainder. So if our message was 2, well, our base that we raised to the power of something, and our mod is 20, then what's going to be the result here? 12, right? So we raise 2 to the power of 5 is 32, mod 20, we end up with 12. And now that our previous algorithm with the binary search does not work because we cannot now compare this 12. Our power could have been 1,000, and maybe it's going to be less than that's 12. So now we broke that binary search algorithm. So are we good now? Does this work? Almost. Here's the problem. Again, I'll need to help from the audience. Tell me the result of this operation. So basically, we always end up either 0 or 6. So instead of figuring out A and B, our attacker can simply try 0 and 6, and one of them is going to be our cipher. So we didn't actually protect ourselves. Well, it's hard to figure out A and B, of course, but we don't need now. We can just try a couple of numbers, and one of them is going to be what we are looking for. So 6 times n is going to be either 0 or 6. 4 times n, I'll tell you, it's going to be either 0, 4, or 8. 0, 4, 8. This is going to be 0, 4, 8, 0, 4, 8. This is going to be 0, 2, 4, basically every even number between 0 and 11. This one, on the other hand, this is a nice one. This one is going to touch every number on the clock. Who knows why? Almost. It's almost there. It's prime, yes. It's what? It's a coprime, right? So it's also prime. Yes, I agree. But the most like intuition behind here is that they don't have any common divisors. No matter which number we choose, if it's not prime, this one is prime or vice versa, they of course will not have any common divisors, but none of them can probably be prime and still be coprime. For instance, 15 and any even number, none of them are prime, but they are coprime because they don't have any common divisors. Well, not every. Yeah, sorry. So eventually what we need is for them to be coprime, and the way to guarantee it is to generate P the way that it's prime. And that's actually everything that we need to protect ourselves. So the full algorithm now looks like this. We generate some random A, we generate some power, Alice generates A, and we also need to generate our modulus, and it has to be prime. Alice calculates this expression, so she raises to the power, but she has to mod it and sends it. And now we send it again modded, so it's not possible to do the binary search algorithm. Bob does the same, also does the mod, also sends it back, and now both sides have the same number. Sorry, yeah, Q also has to be sent over the network. Yes, thank you. It was almost intentional, the error. Okay, so this algorithm is used in security protocols. We have SSH, we have TLS that is used when we do the HTTPS in browser. Before they can do any data exchange, they have to exchange with the keys, and then they start to cipher. That's not all that they need. They also need to trust each other, because it's possible that a man in the middle does not actually send anything to Bob, and you're actually talking to the wrong guy. That problem is not solved by Diffie Hellman. This is a completely different problem, and it's probably a little more complicated than encryption. If you're interested, this is so there are two topics that are often used in cryptography. One is number theory. It's the modular arithmetics, it's the common divisors, it's the prime numbers and a way to generate prime numbers. It's not an easy task. The second topic is abstract algebra. This one is a crazily complicated topic, but basically cryptographists often talk in languages more abstract than what we were taught in school. For instance, Diffie Hellman is not necessarily, it doesn't necessarily work with the powering. We use in this was the first example in the first implementation that Diffie Hellman and Merkley came up with, but there are other implementations, notably elliptic curves, and we abstract away from actual implementation and think and talk in terms of things like groups, rings, fields, commutative operations, inverses, etc. It's a very complicated topic. This book I didn't read, but from skimming through some of the pages, it looked very nice. Any questions?